Evening. My name is Kushal Pisavadia, but feel free to call me Kush. I'm not going to talk very much about myself, but if you want to, you can stalk me on all good social networking there. And I'm here to talk to you about an alternate history of DevOps. Sort of. I have a confession. I've changed my talk entirely yesterday. I've been trying for the last week to make it work, and I've found that the presentation format doesn't quite convey the message that I want to, so here's a very, very quick summary if you were interested. Technology communities are established around tools. Common practices emerge around these tools, and we label them for this community. That'll be the technologies. After applying these technologies, we learn the underlying principles that matter to us. But let's go through an example. So I first learned about this whole DevOps thing in 2009. There are a lot of interesting things that happened in 2009, but to make this really quick, I'm going to concentrate on a very, very small slice of the story. So around 2009, there were two very common tools that existed, Puppet and CFEngine. And they were established config management tools around 2009. And around 2010, this other tool called Chef appeared. It wasn't called Chef back then, it was actually called Marionette. But that's for another time, I think, to talk about. But if you came to this meetup back in 2009 or 2010, one of the really common questions that you heard people ask, or even on main list, if you go back to things like the DevOps toolchain main list, is should I use Puppet or should I use Chef? Another common statement that you would heard is I can already write and test shell scripts. Why do I want this DSL? But essentially, we have these tools, CFEngine, Puppet, Chef. There are other good tools available today. And a lot of questioning from the community of the leaders of these respective tools. And it led to the leaders of these tools essentially denouncing the negativity, saying we're not against each other, we fundamentally want the same thing, and what we now label as config management, and has been, but they just wanted to create a better environment for config management and provide tools for config management. But fast forward a couple of years, and we've now got the principle, which is infrastructure as code. And this now seems really obvious to people, and we forget that there was this weird history associated with it, but this is kind of where a lot of incredibly successful teams are placing themselves. It's this idea of tools, technologies, and principles. And it takes time for us to see these things out. But these ideas aren't new, this idea about tools, technologies, and principles. This idea comes from a term or an area of research called communities of practice. It comes from psychology, sociology, and a whole load of other behavioural areas of research. These labels and terms aren't mine. Etienne Wenger has a great description of what community of practice are. They're groups of people who share a concern or a passion for something they do and learn how to do it better as they interact regularly. That's probably about a good description for us. The main reason for doing this talk is because this thing is everywhere. You've just seen a talk about it, and from my opinion, there's loads of good happening here, there's loads of good discussion, there's a lot of thoughtful discussion going on, but in 2009, this was the question, and today, this is the question. Instead of the previous statement of I can already write and test shell scripts, why do I want this DSL? The modern day equivalent is I can already write and test LXC and C groups, why do I want this API? It's like everything old is new again. And from my point of view, the discourse around these tools should be better. If we're viewing ourselves as a genuine community of practice, then if we're negative around the tools bringing people in, which is why these community practices exist in the first place, then we prevent others from joining in. But that's beside the point, because I've changed my talk. This largely happened because a friend of mine who, in my opinion, she's probably one of the best developers I know, and she said this: I don't need to know about that, I'll wait until X solves it. Now, when I asked her a bit more detail about this kind of statement, she largely said that she didn't feel that she was good enough to understand this particular problem area or why she should care about it in the first place. So I decided to have a go at writing a quick talk yesterday as an introduction. So I'm going to do an introduction to schedulers because it's something that I have been thinking about for years, but loads more people have more recently. Like the boy in The Sixth Sense who sees dead people wherever he looks, whenever I look around, I see schedulers. So let's start from the ground up. The job of a scheduler is to fairly allocate work. Emphasis on fairly. There's a reason for it to schedule work, and it attempts to do it as fairly as possible. There are 3 stages associated with a scheduler: the scheduling, the allocation, and then the binding. Scheduling is where you determine the sequence in which operations are executed. Allocation is where you set aside the appropriate number of functional units for whatever you want to allocate the load onto. And then there's a binding step where you assign these operations to those functional units. 3 stages: scheduling, allocation, binding. So let's look at a really simple example. Arithmetic. So we can try and schedule the expression E equals AB plus CD. If we replace A, B, C, and D with numbers, 1, 2, 3, 4, you might know this sort of form of notation, or BODMAS, if you're from the UK anyway, where you might write 1 times 2 plus 3 times 4. And we know that we have to do the multiplications before we do the additions, or at least that's what we learn. Another way to show this form and this structure is as a hierarchical tree. So here's a very, very quick sketch. You can see that, good. Where you can see that before we can get to E, when we add these 2 values together, we have to multiply A and B and C and D. Now, don't worry too much about the other annotations there. I'll come back to this diagram a few times over. But there are some common scheduling problems that exist. There's the unconstrained problem, where you don't really care about time, you don't really care about resources, you just want this to happen eventually. There's a time constraint problem, where you want it to occur in a number of units of work, or you want it to occur now. There's the resource constraint problem, where you only have a finite number of units for the amount of work you have to schedule. And then the 4th case is a special case at points 2 and 3 there. So let's talk about unconstrained scheduling. Well, it's however you want to do it, really. It's the first scheduling step that you figure out and the order in which you can do this equation. So it doesn't really matter. Now, there's time-constrained scheduling, which is where you might want all operations completed in 2 steps. So in the land of scheduling, everything's referred to as a control step, at least in kind of academic literature. So we might say that we want all work to be scheduled within 2 steps. In this particular case, if you look at the diagram, what we need to do is make sure we can parallelize the multiplication step. So we need 2 units of multiply units, and then a single unit for addition. We might also have a resource-constrained scheduling problem, where we might only have 1 multiplication unit and 1 addition unit. In this case, we would order the events accordingly. So we'd do step 1, where we'd multiply A and B, step 2, where we'd multiply C and D, and then finally step 3, where we'd add and get E around the end. So walk through some common scheduling problems, and these are what most of the academic literature, if you go back to the 70s, commonly referred to, and everything else seems to be built around this. There are other problems, but these are the most common ones. There are also some common scheduling algorithms around this. So there is the ASAP, or as soon as possible scheduling algorithm, which is where you try to allocate the operations of work as soon as possible. There is the as late as possible scheduling algorithm, which, as you might try and guess, is trying to schedule operations as late or as late as possible. There's list scheduling, which is where you try and create a hierarchy. So in the previous diagram where I had 1, 2, and 3, you might create a hierarchy of order, and that's a common choice for solving the resource constraint problem. Or you might have a force-directed algorithm where you weight things. Now, commonly old kind of academic literature around scheduling would weight things according to time, but you might weight things according to, let's say, CPU, RAM, disk, network, and a whole load of other things. There's also another case, which is bin packing, but bin packing is trying to minimize the number of units used by fitting as many things as possible onto a single unit, or you might call them multi-tenant environments, perhaps. So we know the basics of schedulers. Let's try and apply it. Let's look at the Linux kernel CPU scheduler. Just to remind you, the job of a scheduler is to fairly allocate work. The CPU scheduler manages multiple operations and decides which operations get the CPU utilization now. The challenge, of course, is to make sure that applications get a fair share of CPU time, and this is otherwise referred to as a time slice. And there's that word fair again. So the kernel needs to share the physical CPUs among many applications running what appears to be the same time. Now, that's quite hard when a given CPU only has a finite number of instructions that it can operate on in a given time slice. So what the kernel does, or what many kernels do, is a virtualized CPU. You don't get given a real CPU. You can't be trusted. Your applications can't be trusted. The CPU is then happy because it can continue doing what it does best, which is operate on a finite number of operations in a given point in time. And the way this happens is you run one process for a little while, then you run another, and you run another, and so forth. You can actually build something like this if you wanted to, if you know the minimal amount of C, whereby in about a few hundred lines of C code, you can intercept syscalls. So if you're not familiar with syscalls, they're the common calls that any Linux processor would use, things like reading a file, opening a file, closing a file, reading the entries for a directory, opening a socket, closing a socket. You could create a small script, or a small scheduler, which just says, hey, give me the first operation that a process wants to do, and give me another operation from another process, and it's a very, very dumb scheduler. You've made one. So let's look into a little bit more detail around the Linux 2.4 CPU scheduler. There are other good operating systems available. I just happen to know quite a lot about these schedulers. So here's a diagram of a bunch of processes and a log. So essentially this Linux 2.4 scheduler works by normal or other processes, or if you look at the earlier algorithms I went to, they're the kind of force-directed or weighted processes. But the Linux 2.4 CPU scheduler had a number of shortcomings. It wasn't efficient. It had to iterate over all of the tasks and all of the items in the process list. If the process and task list got too big, it would spend most of its time waiting and spinning, just going through this. It was also really bad in SMP, or symmetric multiprocessing environments, or multi-CPU environments. This is because having a single task queue when you've got 10, 20, 30, 40 CPUs isn't great, and you don't end up using all those CPUs, and then people complain why top doesn't look green all the time. So it was rewritten. It was rewritten in Linux 2.6, and it was done by Ingo Molnar. The goal was to handle multiple CPUs better, and to perform independent of loads, independent of how big that process list is. So instead of having this single task list with a single read-write lock over the entire list, it went to multiple task lists. One for each priority, and you'd have 140 queues essentially, each one with its own lock. And this would be the case whether you had, if you had, let's say, 10 CPUs, so you'd have 1,400 queues in existence for the CPU scheduler to work with. That sounds like a lot, but a computer can actually deal with that a lot better than it can a single process list. So we had a bunch of common scheduling algorithms that I talked about earlier, so ASAP, ALAP, list, and force-directed. In the kernel, these have slightly weirder names, or slightly more promiscuous names. Sched FIFO, Sched RR, and Sched other. And you can actually look at all of this information really easily from your terminal. These are kind of like the shorthand terms, so TS, FF, RR. The question mark is for schedulers that have bugs in them, so if you see question marks, be worried. And if you wanted to check, you can just use PS to do this. So you can say to PS, output the class and the command. In this case, you can see that you've got TS, FF are two of the cases that appear, which are Sched other and Sched first in, first out, or otherwise ASAP and list. So if you wanted to, you can actually manipulate these real-time attributes of a process. You might do these with tools like top or htop without even realizing, but the kind of underlying calls would probably interact with CHRT, and you can query for a given process ID, the scheduling policy, and the priority. So, like I said at the start of this sub-talk, I see schedulers. I see them everywhere. You now understand this basic structure, this idea of multiple queues and multiple task lists, and read-write locks. And there is some kind of algorithm that works over this task list. It turns out that exists in other places than just the CPU scheduler. It exists in the networking scheduler. So if you've ever had to deal with the networking layer of Linux, it's a bunch of queues to manage bandwidth. And all of the terminology around this is around queues, is around queue disciplines, queue algorithms, and locks. So if you've ever dealt with IP route 2, IPSEC, or multicast routing, all of these are backed by a scheduler. And you have the basic fundamental knowledge to apply and understand how these things work. There are other schedulers, like the memory scheduler, for example, or the graphics card you might or might not use, depending on how weird your OS of choice is also run largely by a scheduler. If you use a database, there's probably a scheduler in there. If you take Postgres, there's an auto vacuum process that runs, which is in and of itself a scheduler to do compaction. And maybe you write some application code which uses the CPU, the RAM, the GPU, maybe writes some data into Postgres, and maybe your application runs baggage claim at many of the airports around the world, which are essentially loads of queues of blocks. That thing, again, is everywhere, and there are loads of schedulers there. So if you take Kubernetes, the interface or the API expects you to take a given pod, I don't really get this wording, but a given pod and schedule it over a bunch of minions. Or Docker Swarm is essentially the same thing, where you place a container over a bunch of nodes. It's essentially the same interface. It doesn't really make a difference. But again, I see schedulers wherever I live. And the job of a scheduler is to fairly allocate work. But there's another scheduler that I've not really talked about that I see whenever I look around. There's the person that wrote the code. They would have scheduled their own time, and they would have worked out fairly what they thought was the best thing to do. They might have had an algorithm, whether it's Pomodoro, brute force, time constraint, resource constraint. There's the person that planned the work, who would have figured out how to sequence all of these units of work across all of the operational units. And then there's the scheduler that wants the work done. They would have tried to describe and define the sequence of work they wanted done in a way that is easy for everyone else to take on. But why are we so willing to trust software but find it harder to trust the people around us? We as a community look at all of these schedules like Kubernetes and Swarm, and fundamentally, if you're a sysadmin or an web operations person, you probably do this yourself. You're probably asked to deploy an application into an environment and work out the best way to do it, to define the resource constraints. You might be asked to do the job of like figuring out how to correctly, in terms of availability, shard a SQL database, and that's something that we are way too willing to give off to these schedulers, which at the moment are really dumb. But I see schedulers wherever I look. So how much of the work we do is actually a device to help us focus on what's really important, to be fair to us and those around us. That's it. Thanks for scheduling your time with me.